Alright, silly people, here's the situation. We're going to be proving that the expectation value of x for a given wave function in momentum space here is just given by that momentum space wave function times I h bar del del p times the momentum space wave function, and it's conjugated on the left-hand side. Right? Uh, and to do this, I'm going to just start with the the position space definition of the expectation value of x. So that's the integral from minus infinity to infinity. That's the bounds of all the integrals that are going to be in this problem. But it's psi star x psi dx. And then just before this problem, there was a bit in the book where Griffiths expanded the position space wave functions in terms of the momentum space wave functions using inverse Fourier transforms. So that's what I'm going to do, and I'm going to write the dx out here. Psi star of x will be given by just quoting what the equation was saying. It's 1 over square root 2 pi h bar e to the I p x over h bar, momentum space wave function p of p and t dp, and then you have to conjugate all that. We still have the x laying around from before. Whoops, and then we also have to do a psi of x on this side, so that's going to be 1 over root 2 pi h bar. Integral e to the I kx over h bar phi of k and t dk. And I'm using different labels for momentum here in each expansion of the position space wave function, just because there's kind of a mathematical precedent to do so here. They're going to end up being the same via a delta function anyway, so if that freaks you out, don't worry about it. We'll show that the momentum is the same. And then we're going to pull out all of our root 2 pi's h bars out here, so it's just 1 over 2 pi h bar on the outside of all the integrals. Doing the complex conjugate there, it's integral dp e to the minus I px over h bar phi star of p and t. We still have an x, and then we've got our integral dk e to the I kx over h bar phi of k and t. Right. So Griffiths wanted you to notice something in the problem statement. He was very generous with the hints on this problem. He said, notice that x e to the I px over h bar is equal to minus I h bar del p e to the I px over h bar, which is true. That's just extracting a derivative from what we have. So we have an x here. We have it multiplying an e to the I kx. So we're going to use this here to rewrite at least the part of the integral that involves the x and that exponential to be a derivative, because it's funny. So this is now dk minus I h bar del p acting on e to the I px over h bar, and still multiplying the phi of k and t. Right. But we don't want the derivative acting on the exponential. We want it acting on the momentum space wave function. So we're going to have to do integration by parts. First of all, I'm going to move that minus I h bar out of everything. So we've got minus I out here, just over 2 pi of the junk. And then I'll write all this stuff out again so that we can clearly see, what we have to have be our u, and which is going to be v. And I'm even going to write the 5, k, and t on the left, just so we're keeping track of the fact that the only thing that the derivative is acting on is the exponential here, right? And it also should be k, most assuredly, in both of these lines instead of p, because that's how we're labeling our momenta on this side of the integral. Fantastic. Okay. Now, integration by parts time. I'm picking u equals phi of k and t, and so du will be del k of phi of k and t dk, and then dv will be the del k of e to the I kx over h bar, so that the v will just be e to the I kx over h bar, right? So doing the integration by parts thing, we still have all of these factors out here. The e to the minus ipx over h bar, phi star p of p and t times, and I should have left myself a little bit more room, but it's okay. In brackets here, uv, so phi of k and t e to the I kx over h bar, evaluated at minus infinity to infinity, minus the integral dk v du, so it's just e to the I kx over h bar del k phi of k and t. And then the bounds of that integral are still minus infinity to infinity. So, as always, whenever you evaluate a wave function, it doesn't matter if it's in position space or in momentum space. It should be 0 at the endpoints, so we can very much cancel out that term that came out of the integration by parts. And so we pick up an extra minus sign, which we're going to move all the way out front. So we're going to have just I over 2 pi integral dx integral dp e to the minus I px over h bar phi star of p and t times the integral dk of e to the I kx over h bar del k phi of k. Now, the cool thing about this is that now all of the things that depend on x are just tied up in those exponentials, so we can move the integration with respect to x all the way to the right. So we've got the integral dp phi star of p and t integral dk of the derivative of phi of k and t, still just a derivative over k. I'm getting exciting. Dx e to the ix over h bar, and it's ix times k minus p here over h bar. Okay. We're going to massage this integral a little bit using u substitution now to get it into the form of equation 2.147 in the textbook. So if you do that, we're picking u equals just x over h bar, so that du is dx over h bar, or in other words, dx is h bar du. So we're picking up another factor of h bar that we're going to move all the way out front for now. So we got I h bar over 2 pi integral dp 5 star of p and t integral dk del k of phi and k and t. And then the remaining integral here is just du e to the iu k minus p, which means that using equation 2.147, the result of that integral is just 2 pi times a delta function. So we are going to have one of those. It's getting real close now. 2 pi delta function, and it's k minus p is the argument of it. The 2 pi cancels out the 2 pi, and we can move the IH bar into the derivative term just because we can. And acting the delta function, using it to complete the dk integral, just replace k's with p's. So we've got IH bar del p of phi of p and t, and you're done. So that's was kind of the goal. I think also he put the outer parentheses here, but whatever. And all this is to show that, the x operator in position space is given by IH bar del p, kind of like how the momentum operator in position space is minus IH bar del x. So it's kind of a cool symmetry there, and also that's just a cool problem in general. So neat.